Okay, so hi everybody. So today we're going to go through the proof of the theorem of highest weight for SL3. So doing the analog of what we did in the SL2 case. Okay, so let's just review the statement of the theorem of highest weight, and then we'll go through the details of the proof. Okay, so the first statement here is that every SL3C irreducible representation is the direct sum of its weight spaces. Okay. So analog of the root space decomposition, but in the setting of a general irreducible representation, okay, of SL3. Second statement is that every irrep has a unique highest weight, okay? And moreover, it's dominant integral. Okay, so that means that if I take that weight and then write it out in terms of the fundamental weights, then these coefficients are going to be non-negative integers. Okay. Pictorially, it's saying that we're in the so-called fundamental Weyl chamber. Okay. But the integrality says that we're only at certain, we have to lie on certain lattice points that lie in this fundamental Weyl chamber. Okay. So non-negative linear combinations of these fundamental weights. Third statement, two irreps with the same highest weight are isomorphic. Okay, so from this discrete data here, we have a complete classification of these irreps. Okay. Or rather, we need the fourth statement about existence. So if you have a dominant integral weight, so something lying in this fundamental Weyl chamber on one of these lattice points, okay, these lying on this weight lattice, then there does exist an irreducible representation with highest weight, mu. Okay, so to summarize here, SL3 irreps up to isomorphism, okay, correspond to weights that are dominant integral, which we encode on a Dynkin diagram just by putting the corresponding coefficients over the corresponding fundamental weights. Okay, and sometimes we'll also use this notation right here for that highest, also for that irrep with that highest weight. Okay, so let's go through some of the details of the proof. Okay, so it's going to be broken up into a series of propositions. Okay. Okay, so let's start. Okay, so the first proposition is if you have a G irrep. Okay, so here G is SL3C for concreteness, since we haven't played around too much with other semi-simple Lie algebras, but basically the proof is going to be exactly the same. Okay. For the other ones. So if pi v is a G irrep, then V is a direct sum of its weight spaces. Okay. Okay, so this one is a pretty short one. So let's go through the proof. Okay, so let's W be the, so this is a subspace of V, be the sum of all weight spaces of V. Okay. So this is a non-trivial sum, right? Because we are working over C. Okay. So we've seen this argument before that there exists at least one weight. How do we know that? So take anything from the Cartan subalgebra. So let's say H. Okay, we apply pi to it. This is an endomorphism of V, and we're working over C. So this specific endomorphism over C, this linear operator, has an eigenvalue. Okay, but that's for one specific element, H from the Cartan subalgebra. But via this trick of simultaneous diagonalization, if you pick any other one, then you're going to get the corresponding eigenvalue there. And so we're going to generate a weight out of this simultaneous diagonalization. Okay. So, right. So you do have at least one weight. So this is a non-trivial subspace. Okay, W. Okay, so the claim is that W is G invariant. Okay, so how do we check this? Well, first start by what's the action of the Cartan subalgebra? Well, W is a sum of all weight spaces. Okay, and on each weight space, you know that the action of the Cartan subalgebra is really easy. It's just going to rescale within that weight space. So each weight space, let's call it V mu, is H invariant. Okay, but W is the sum of all of these, so therefore W is also H invariant. Okay, so that's for the action of the Cartan subalgebra. Next, well, we know that we have for G is the direct sum of H and a bunch of root spaces. Okay, that's the root space decomposition. Okay, so next we have to ask, okay, how do those act? So for any roots, recall that we proved something last time, that if I hit it with the representation, okay, so this pi E alpha is a root vector, okay, so E alpha is in the corresponding root space, but this pi E alpha is a endomorphism. We saw that this acts on a weight space, V mu, to lie inside V mu plus alpha. Okay, so if this is non-zero, then this is going to be a weight space. Okay. So, but it could be zero. That is also a possibility. Okay, but if this is non-zero, this is saying that this operator is moving this weight space into another weight space. Okay, but W is the sum of all weight spaces. Okay, so this pi E alpha is sending W into itself. Okay, so W is pi E alpha or G alpha. So this guy is invariant under this action. Okay, so finally, from the root space decomposition, we conclude that W is non-zero G invariant subspace of V. But by hypothesis, right, we're working inside an irreducible representation. So W is a G invariant subspace in here. So since V is irreducible, so W has to be equal to V, right? We know that W is non-zero by hypothesis, right? Those are the extreme cases in an irreducible representation. Either you have an invariant subspace so that implies that it's either a zero or the full thing. Okay. So it's not zero here, so it has to be the full thing. Okay, so that's the first statement here. Okay, so if you have an irreducible representation, V is the direct sum of its weight spaces. That was the right. That was the first statement in the theorem of highest weight. Okay. Next, before I formulate the proposition, I want to motivate it. Okay, so the motivation here is to ask, is there a weight mu that acts as a seed for the representation? Okay, so just like in the SL2C case, you have this non-negative integer m, okay, that is going to act as this highest one, and then from all of this, the entire representation can be generated. Okay. Just like in the SL2 case. Okay, so this is something that we want to prove. It's in the statement of the theorem of highest weight, but we have to prove it, and so we shouldn't assume that that you have highest weight, right? That acts as such a seed. So you have to formulate a concept that asserts this, right? So a setting. Okay, so the definition that we want to that is going to be useful here is the following. So pi v is a highest weight cyclic G-rep with weight mu if there's a non-zero vector such that this vector is in this weight space V mu. If I hit it with any of these positive root vectors, okay, under the representation, then I'll just get 0. And 3, V is the smallest G invariant subspace containing V. Okay. So this is our notion of a highest weight cyclic G-rep with weight mu. Okay. Right. So so the first proposition associated with this concept, well, first of all, where are we headed? We want to show that any irreducible representation is one of these highest weight cyclic G-reps with weight mu. Okay, and conversely, any one of these guys, highest weight cyclic guys, is in fact irreducible. Okay, but there's something to be shown here. Okay, that we don't want to assume that these are the same things. Okay. So what can we say about this definition? Okay, this object. Let's pi v be a highest weight cyclic, with weight mu. Okay, so first, there's no assertion in this definition that mu is highest, right? So we do want to say that pi has highest weight mu. Okay, and there is something to be shown here, right? These first two bits say that if you take anything from a positive root space, a positive root and the corresponding positive root vector, then it will kill this, this vector with weight mu. Okay, but being highest, remember, means that everything in the representation is comparable to that highest weight and is less than or equal to it. Okay, so there is something non-obvious because that's not in the definition. Okay, so that's something that needs to be shown. Next statement is an important fact that for any highest weight cyclic, I should say G rep. Okay, the dimension of this V mu weight space is 1. Okay, so this is a formulation, and so we want to prove it, but we'll need a lemma first. Okay, so this is called the reordering lemma. Okay, and I'll put this, let's see, let's call this proposition star, say, we'll come back to that. Okay, so reordering lemma. Let's go green. Okay, so this is a slight technical lemma. It's not difficult to prove, but let me just formulate it, and then we'll see how to apply it after the proof. Okay, so let G be any Lie algebra, and this pi v a G rep. Okay, suppose I have a basis. For G. Then let's consider the product of, oops. So the product of some of these operators here. Okay, so I'm going to look at the product of these pi xj i's. Okay, it's an infinite number of them. So the statement here is that this is a linear combination of terms like this. Okay, so I have a fixed, I've chosen some ordering for that basis. Okay, if I take some collection of those xj's, okay, then I could reorder it and write it in this form. Okay, so for that chosen ordering here, I could write it as a bunch of x1s first, then a bunch of x2s being acted, then all the way up to xm's. Okay. For some kr greater than equal to 0, and some of these guys less than or equal to n. Okay, so you could write this guy as a linear combination of these guys. Okay, there's n of these appearing over here, and these expressions, right? There is at most n applications in each of these terms. Okay. How are we going to use this for establishing this one? Basically, the idea is to use the root space decomposition. Okay, we have positive root spaces, we have the Cartan subalgebra, we have negative root spaces. We're going to reorder, so then we're going to hit a V in this weight space with weight mu, with the positive ones first, then the H's in the Cartan subalgebra, and then the negative ones. Okay, so I'm skipping ahead a little bit. So let's prove this result first, this reordering lemma, and then we'll apply it. Okay, so this is going to be an induction proof on n. For n is equal to 1, we're good. Okay, there's nothing to prove. So let's suppose it holds for general n. Okay, so we need to show it for terms that are an application of n plus 1 of these guys. Okay. So it holds for general n by hypothesis. So what we're going to do is, so we have n plus 1 of these, we're going to apply it for the last n factors. We're going to apply induction hypothesis to the last n factors. So what we're going to get out of this is that we have this whole thing written as a sum of the following. Okay, so terms of the form, so pi xj, actually xj1, I guess. Okay, then pi xm k1, pi x1, oops, sorry, km over here. Okay, so we get a bunch of terms of this form, okay, where the sum of these ki's is less than or equal to m. Okay, so and actually, instead of putting this j1 here, I'll just put xj here. It doesn't really matter. So something of this form. Okay, so what we're going to do is we're going to rewrite this. Okay, so this xj is one of these guys over here. Okay, so we want to start moving this to the right. Okay, so how do we do this? So we use a trick that we've seen many times before. Okay, so every time you try to push it past, it's gonna be at the cost of a commutator. Okay, so let's get a notation for this commutator and start moving things. Okay, so we have pi xj, and then let's suppose we want to push it past pi xr. Okay, so you could rewrite in the opposite order, but at the cost of a commutator. But then we use the homomorphism condition to rewrite this last term as pi of a bracket. And then we bring in the bracket relation, okay, that we have over here. Okay, so we have pi xr, pi xj, plus You put in the commutator relation, you take the constants, the coefficients out. That's what you're left with, is this. Okay. So what we're going to do is just use this repeatedly on this term over here. Okay. So apply this repeatedly above. Okay. So in doing so, all commutators have at most n factors. Okay. So for these, we can use the induction hypothesis to write them out. Oops. To write them out. Okay. Keep pushing this pi xj to the right as necessary. Okay. And so that gives the claimed result. Okay. So again, let's look at the statement of this. Okay, we have this reordering lemma. Okay, we have a chosen basis with a certain ordering. Okay, let's choose some. The statement is that if you have pi of some selection of these, okay, you could rewrite it as a linear combination of these terms. Okay, so x1s first, then x2s, all the way up to xm's. Okay, so in that order, where the the number of these terms is at most n. Capital N is how many of these operators are being used in the first place. Okay, so now we go back to our proposition now that we want to prove. Okay, we have a highest weight cyclic G-rep with weight mu. Pi has a highest weight mu, and the dimension of this top weight space is 1. Okay, so let's go ahead and apply this now repeatedly. Let me insert a new page. Okay, so apply to proposition star. Okay, so let's take V in this weight space for mu. Okay, and we're going to define a subspace. So this is a subspace of V. Okay, so it's going to be the span of all the vectors of the form. Well, let's hit this V with a bunch of negative root spaces. Okay, so here, these beta i's are positive, but I've put some negative signs in here. Okay, and n here is arbitrary. Okay. So we want to use this reordering lemma. Okay, and so remember the root space decomposition says that G has basis. Well, you have a bunch of positive root spaces. You have the Cartan subalgebra, which is spanned by these H's. Okay. Yeah, let me write H alpha I. okay, where I goes up to the rank. And then you have negative root vectors. Okay, root vectors from the negative root spaces. Okay, so we're going to let any of these basis elements act on one of these W's from above. Okay, so by reordering, what can we say? So we can rewrite as a linear combination of stuff that looks like the following. Okay, so you have a bunch of negative stuff. You have oops, some of these H's. And then you have some positive stuff. Applied to V. Oops. Oop, not good. Let's try that again. Okay. So I've used reordering to do this. Okay, so these so here gamma I, let's put it, it's positive stuff. These beta J's are also positive. Actually, let me just get this out of the way. Okay. But in doing it in this order, you can see what's going to happen here. So if you have any non-zero, non-trivial number of these positive things that are being applied to V, well, by definition of working within a highest weight cyclic representation, positive stuff will kill V. Okay. So if L is strictly bigger than 0, then this will be 0. Okay. Otherwise, if you go to the next batch of stuff, you have these H's acting, but H just rescales V. So under the application of all of this stuff up to here, this is a multiple of V. Okay. So this is a multiple of V, and then you have negative stuff. Sorry, bad notation. I guess I've repeated these betas as these original betas, but they may in fact be different. Okay, so let me just, let's put beta tilde. Okay. So W was the span of all these terms over here, V, and then you hit it with negative stuff. This results, once you let one of these basis elements act on this W, you use reordering to rewrite it in this form, which you notice is a multiple of V, and then you hit it with some negative stuff. So by definition, it's still in that subspace W. Okay, so therefore W, oops, sorry. W is G invariant. It's a G invariant subspace. It's non-zero, so therefore W is V by irreducibility. Okay, so finally, what about it being the highest weight and mu being the highest weight and of dimension 1? So if n is bigger than 0, either w is equal to 0 or w has weight strictly less than mu. Okay, so if you've applied at least one of these guys, then yeah, you're going to drop. So right, remember this n is over here. Okay, so if there's a non-trivial number of negative root spaces that are being applied to this, well, you're shifting to a different weight space, and that weight space, that weight for that weight space is strictly less than this top one. Okay. So therefore, the dimension of V mu has to be just equal to 1. Okay. And so we're done for that. Okay, so we've just shown that if you have a highest weight cyclic representation with weight mu, then pi has highest weight mu, and the dimension of this weight space is 1. Okay, next proposition. Okay, so we have a few more small propositions to go. So the next proposition is that every finite dimensional G irrep pi v is highest weight cyclic rep with a unique highest weight mu. Okay, so we know that V is the direct sum of a bunch of weight spaces. Okay, so that was already shown. Which is, well, we know this is finite dimensional by hypothesis. Okay, so this is finite dimensional. So we have finitely many weights. And we have a partial order. So we have finitely many weights, a partial order. So there exists a maximal weight, mu. Okay, so maximal is not the same thing as highest. Okay, so what does maximal mean? So i.e., no other weight nu for the rep is higher. Okay. We aren't assuming uniqueness here. Okay, there could be several maximal weights. Okay, but okay, so we have one maximal weight. So let's take a vector in this weight space. Well, if we take, so this is highest weight cyclic, and we start hitting it with positive stuff. So given a positive root, we know that if we hit pi e alpha on V, then that will land over here in this V mu plus alpha. space. Okay, but this guy is not a weight. Why? Because mu plus alpha is certainly well, strictly bigger than mu. I should formulate this as so maximal in the sense that no other weight nu for the representation has strictly bigger weight than mu. Okay. So here you have something that is strictly bigger. So necessarily by mu being maximal, then this cannot be a weight. Okay, so therefore, this weights, well, it's not a weight space, right? This v mu plus alpha is equal to 0. And therefore, this guy is also 0. But we know pi is irreducible. So since pi is irreducible, and so the smallest G invariant subspace containing V is necessarily V. So therefore, the rep is highest weight cyclic with highest weight mu. Okay. There was a statement about uniqueness, but yeah, basically, if I had a mu prime that's also a highest weight here, then you have two relations. Mu is highest, so mu is bigger than or equal to mu prime, but mu prime is highest, so mu prime is bigger than or equal to mu. So therefore, they have to be the same. So we'll say uniqueness is immediate. It follows from definition of being highest weight. Okay. Okay, so right, so we've just shown that every finite dimensional G irrep is highest weight cyclic, okay, with unique highest weight, mu. Let's go in the opposite direction right now. So let's pi v be highest weight cyclic with weight mu, okay. Then pi is irreducible. Okay, so we already know that this being, so if we have this phrase, highest weight cyclic with weight mu, then we've shown in a proposition that this is actually a highest weight, okay? So I'll put this in parentheses, it follows, okay? So why is this thing actually irreducible? So complete reducibility says that V is the sum of a bunch of irreps. Okay, a bunch of VJs. Okay, but we know from proposition, okay, so one of these propositions we just proved, each of these VJs is a direct sum of weight spaces. Okay. And this highest weight, this weight mu, so it occurs in in one of them. So in some Vj. Okay. We also know it's multiplicity. Okay. Each of these Vj's is irreducible. So that implies that the smallest G invariant subspace containing, well, the weight space in Vj with weight mu is Vj itself. Okay, so that's just a straight out application of irreducibility of Vj. But remember that by definition of V being highest weight cyclic, with weight mu, the same concept here, the smallest G invariant subspace containing Vj mu is V itself. Okay. So these two things have to agree. Vj is V. Okay. But each of these Vj's is irreducible. Okay. So therefore, V is irreducible. And we're done. Okay, getting there. Okay, so it's basically two more things. Okay, we want to show that if you have two erups with the same highest weight, then these are isomorphic. And the last part of the theorem of highest weight is that if you have a dominant integral weight, then there exists a corresponding irreducible representation. Okay, we know from stuff before, we already described that dominant integrality is a necessary condition coming from SL2 theory. Okay, so right, these two remaining propositions. So two G erups with the same highest weight are isomorphic. Okay, so this is going to be a nice application of Schur's lemma. Let's take two G erups. With the same highest weight mu and weight vectors V in V mu and W in W mu. So we're going to consider the sum V plus W. And the smallest G invariant subspace U inside this v plus w, containing the vector v plus w. Okay. So right. This guy is in the highest weight space. It gets annihilated by the action of all of these operators coming from positive root spaces. And then I generate the smallest subspace that's invariant from this seed data. Okay, so therefore this this U is highest weight cyclic. And we showed that these are irreducible. Okay. Okay, so U is irreducible, V is irreducible, and W is irreducible. Okay, we need to get some maps between them and then apply Schur's lemma. Okay, so we have projections P1 and P2 going to each of these factors. Okay, so the natural projections. Straightforward to see that these guys intertwine the G action. Okay, these are intertwiners. Hence, so are the restrictions. Okay, restricting to U. Certainly these are non-zero maps because since on this vector, which is inside U, well, the projection is non-trivial. So they are non-zero on W. And now is where we kick in the this Schur's lemma. So since what we're dealing with is a bunch of irreducible representations, so U, V, W are all irreducible, then Schur's lemma implies that P1U and P2U are isomorphisms. Okay. These maps go from irreducible representation to target being an irreducible representation. Okay. They are non-zero maps. So Schur's lemma tells you that they're isomorphisms. So V is isomorphic to U, which is isomorphic to W via these maps. Okay, and so we're done. Okay, so any two G E-reps with the same highest weight are isomorphic. Okay, so lastly, we need to assert the existence. We did a little bit of this last time. I guess some of this is repetition, but just for the sake of this video, let's recall some of this. So recall if pi is a G irrep with highest weight mu, then mu is dominant integral. Okay. Need to assert the converse. So to do that, so for a weight A lambda 1 plus B lambda 2, well, let's start with the fundamental reps. Okay. Okay, so fundamental E reps Okay, so if the highest weight is a fundamental weight, so lambda 1 or lambda 2 for SL3, okay, we've constructed these as standard representation and the dual standard representation. Okay, this is highest weight E1, referring to a basis E1, E2, E3. And then the dual has highest weight E3. Okay, so from these fundamental EREPs, we're going to construct the general SL3 EREP via, taking tensor products. Okay, we're going to find the corresponding irreducible representation in some tensor product space. So if mu, which is a lambda 1 plus b lambda 2, sometimes so encoded by this Dynkin diagram notation AB. So if this is dominant integral, then there exists an SL3 EREP pi AB. With highest weight mu. Okay. So we induce the SL3 rep pi AB. Oh, actually, I guess we want the, let's not use this notation there. Induce the SL2 rep on V being the 8th tensor power of the first fundamental EREP, the bth tensor power of the second, and then you tensor those together. Okay, so then if I take the corresponding highest weight vectors, okay, so there's A of these over here, B of those over there. So this is the highest weight vector with weight mu. Okay, mu being a lambda 1 plus b lambda 2. Okay, but this V constructed this way, it may decompose into a bunch of irreducible representations. Okay, but there's going to be, exactly one inside here having this highest weight. Okay, so let W be the smallest G-invariant subspace containing V. Since V is completely reducible, then W is 2. It is highest weight cyclic. And we know highest weight cyclic things are irreducible. Okay, so we found inside this tensor product space a copy of an irreducible representation with highest weight a lambda 1 plus b lambda 2. Okay, so we've now constructed this irreducible representation with this highest weight. And so we've proven existence. Okay, and that concludes the proof of the theorem of highest weight.